Okay, so we have talked about systems of equations. A system of equations contains two equations. The ones that we're doing has two equations, and each equation has two variables. Okay? And we talked about how to use systems to solve problems, and we talked about using them to set up a problem and to verify. So now the question becomes, how do we actually solve them instead of just me giving you what the solutions are and you checking? So there's three different ways. And the first way is by graphing. So you guys should be pretty good with the graphing by now, graphing lines. So let's graph this system of two equations. And remember, you got three methods to choose from. So let's call this one number 1, and this one number 2. How would you like to graph number 1? How? So you want to put it in y equals mx plus b form? Sure. And really, there's only one step to do, is to take the 2x over to this side by subtracting 2x. So that gets rid of it here. So we get y is equal to negative 2x, because you write the x term first, minus 4. Well, now what? So y-intercept is negative 4. Put that on the y-axis. And then? Right, so you'd go down 2 and over 1. And it would look like this. Okay. All right. How would you like to graph the second one? Table of values? I suppose. Is there something easier? Can't I just do slope-intercept again? You guys should get used to using slope-intercept. But table of values will still work. Okay. So what's the y-intercept for this one? Negative 1. And what's the slope? As a fraction, 1 over 1. So that means from the y-intercept, I rise 1, so up 1, run 1, so to the right 1. And I get this. At what point, if you drew them exactly, do they intersect? The two lines. Negative 1, negative 2. So they intersect at x equals negative 1 and y equals negative 2. Interestingly, if you were to put these two values into the two equations, you would see that the left side equals the right side, which means this is the solution to the system. So if you look at this one here, if we check this one, 2x plus y is equal to negative 4, we had x as negative 1 plus y is negative 2, negative 2, negative 4. Well, does 2 times negative 1 plus negative 2 equal negative 4? This is negative 2. This is minus 2. Yeah, it does. So that means that the points of intersection I found work in the first equation. Do they work in the second equation? Well, does negative 2 equal negative 1 minus 1? Yes, it does. So you can see that to find the solution to a system by graphing is just graph each equation, find where they intersect, and those are the values of your two variables. That's it. So you could write your solution like this, x equals negative 1 or negative 2. Sometimes you can see solutions written like this too. You could write it as a coordinate. Both of those are correct. If you wrote it, if I asked you to solve the system and you wrote your final answer like this, it's correct. If you wrote your final answer like this, it's correct. I want you to try the next one. Remember, you can do any methods you want to graph them. Like, who knows, maybe some of you for the first equation might use the intercepts. Or you might just move the x over and do slope intercept. That's fine. All of those are fine. So go to it. See if you can do it. What method did you use for this one? Okay, so to use slope intercept, we've got to bring the x over with the 8 by subtracting x, and we get y equals negative x plus 8. That tells us that the y-intercept is 8, and the slope, rise over run, is negative 1 over positive 1. For the second equation, we've got to bring the 3x over by doing minus 3x. So we get negative 2y is equal to negative 3x plus 14. I must divide everything by negative 2 to get y by itself. Oh, what's the easiest way to say this? 3 over 2x. And the easiest way to say, whoops. And the easiest way to say this? Negative 7. Okay. So here our y-intercept is negative 7. Our slope is a rise of 3 over a run of 2. So now as long as we plot everything correctly and count our slopes out correctly, we should get the point of intersection. So for the first, I'll do the second one first since I'm already in purple. So I get negative 7, 2, 4, 6, 7, up 3 over 2. And then it's going to look like I believe it looks like that. My other one, y is equal to negative x plus 8. So 2, 4, 6, 8. Down 1 to the right 1. And that should give me a nice point of intersection, no fractions, at the point what? 6, 2. So you can write your final answer as 6, 2. or you can separate it by doing x equals 6, y equals 2. Okay? Now, how can we actually use these to solve problems? So let's look at a problem. One plane left Regina at noon to travel 1,400 miles to Ottawa at an average speed of 400 miles per hour. Another plane left Ottawa at the same time to travel to Regina at an average speed of 350 miles per hour. A linear system that models this situation is given. Okay? So one of them, does this represent the plane that's going from Regina to Ottawa or Ottawa to Regina? Sorry? Why? Yes, and the speed is 400, which means the equation must have 400 in it. So yes, this is Regina to Ottawa. Which means this must be Ottawa to Regina. And that makes sense because D represents the distance from Ottawa. So when the plane takes off from Regina, it's 1,400 miles away from Ottawa. But then every hour, the distance gets 400 miles less. This one leaves Ottawa. Well, its distance from Ottawa when it leaves is 0 because it's at Ottawa. And then it starts traveling to Regina. Every hour, it puts on 350 miles. Okay? What we want to do is we want to graph this system. And from that system, we want to see when did the planes pass each other. And just so we're clear, so somebody doesn't ask the question, they're at different altitudes. Okay? They will cross each other at different altitudes. So please don't ask them. I mean, they're going to hit each other. Not in 3 dimensions. Okay? All right, so what I want to do, you got to think of these like y and x. Well, I'm going to rewrite this one so that it looks like this, because that's the way we're used to seeing it. Because this is y equals mx plus b form. This is already in y equals mx plus b form. It's just there's no y-intercept. Okay? So here, the y-intercept, although technically it's called the d-intercept, would be 1,400, and the slope would be negative 400 over 1. With this one, the y-intercept would be 0, and the slope would be 350 over 1. So I've got to graph those. Everything's going to be positive. Time and distance are going to be positive. So I don't need to do all 4 quadrants. I only need to graph the first quadrant. So I'm going to do this. This just represents the first quadrant. And that's the origin, 0, 0. So this represents the time, t, and the vertical represents the distance, d. What are the possible values for time? How should I set up my scale? Well, the question is, What's the highest amount of time I'm going to get? How much? 100? 400? Well, no, not 400, because it's 400 times the time. If I traveled for 1 hour, if I traveled for 1 hour, would you all see that I now have 1,000 miles to go? Because 400 times 1 is 400, 1,400 minus 400 is 1,000, right? So after 1 hour, after 2 hours, how much? Remember, I'm at 1,000 miles now. 600. After 3, 200. After 4, well, I've already landed, haven't I? So I only really need to go up to 4 hours, don't I? But I don't want to go 1, 2, 3, 4 because then my graph is going to be really tight. So what I'm going to do is every second notch or grid line, I'm going to call 1. And I don't have to go any further. I mean, I put 5 in there, but I don't have to go any further than 4 because this thing's going to be over before 4 hours because the flights are going to be done. What should I put for the distance, though? Now the distance, that's different. Because here, like when this plane is sitting on the, or sitting at Regina Airport, how far is it from Ottawa? 1,400, right? So I have to go up, my vertical scale has to go up to 1,400. How much should I go up by to make sure I get to 1,400? 200 or 500? Yeah, so we could go up by, we could go up by 100s, couldn't we? Do we have enough? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1,000, 1,100, 1,200, 1,300, 1,400. That would work. But I'm not going to label every one. I'm going to label every second one. You don't need to label every one. And I'll do one extra. And now let's graph each one. And I'm going to graph this red. No, sorry, I'm not going to graph that red. I'm going to graph this green and this blue. And then I'm going to circle the intersection in red. What's the y-intercept of this? 1,400. So for the green one, on the y-axis, it's here. And what's the slope? Negative 400 over 1. So that means from here, I have to go down 400, which means I go down to 1,000. And then I go to the right 1, which means I have to go over 2 grids, because we call 2 grids 1. So it's actually here. So really, I'm going down 4 and across 2, down 4 and across 2, down 4 and across 2. Here's another question. Do I put arrows on the end of these? Why? Yeah, because it ends, and it starts at a certain point, and it ends at a certain point. It doesn't go on forever. I mean, you can't have it going this way. You can't have an arrow going this way, because then you're going into negative time. That doesn't make any sense. If you have it going down, you're going to have it going into negative distance, which makes no sense. How about for the second one? What's the y-intercept? 0. And the slope? Right, so this one's going to be a little tough. So that's 300, 350. It's going to be somewhere about there. So I'm going up 3.5 notches and over 2. Up 3.5 notches and over 2. Up 3.5 notches over 2. Up 3.5 notches over 2. Notice I can just keep counting points using the slope. And I end up with that. And again, I'm not putting arrows on the end, and I'm stopping at 1400 because that's the length of the flight both ways. Well, I'm not going to get a nice clean answer. If you graphed as accurately as possible, what would we be approximately? Like, what would be the time that they cross each other, and what would be the distance from Ottawa that they cross each other?
An hour and a half.
Hour and a half? Mine is a little over an hour and a half. But if you're on an hour and a half, fine, because we're approximating. Okay? So, question asks, when do the planes pass each other? How far away are they from Ottawa? We would say they pass each other after. So if you figure out what you got from your graph. If you drew it exactly, I mean, if you're using a ruler, better. Mine looks like it's about 1.7 hours. That's mine. Yours may look a little different. Go by yours. But mine looks the same. For distance, mine looks the same as yours, 650. They pass each other after 1.7 hours and are 650 miles from Ottawa. Technically, I should put about for each. After about 1.7 hours and are about, because I'm kind of estimating a little bit from my graph. So, yeah.
Instead of saying 1.7 hours, you say like 1 hour and like 15 minutes or like 1 hour and like 40 minutes.
As long as you know how to convert properly, right? Because, let me ask you this. Convert to hours and minutes, 1.5. How many hours and minutes is 1.5 hours? How many hours and minutes?
Wait, an hour and 30.
1 hour, 30 minutes. Okay. No, I said hours and minutes. Okay. How many hours and minutes in 1.75 hours? Okay, so now you're getting it. Because some students, what they do is they just read the decimal as the minutes. So they would say, like, if I said 1.3 hours, they'd say 1 hour, 30 minutes. Okay. It happens sometimes. Okay. I mean, it's like I'll bet you there's got to be at least some people. If I asked you to turn around and read that clock, you wouldn't be able to. I could be wrong. Okay. Yes, because you're looking at your phone.
Who said that?
I did, because your eyes were like this.
Maybe I was looking at your desk.
Oh.
You're so rude, Mr.
What? I don't know what that means. I don't know why do you hurt me? Why do you hurt me? Okay.
No need to stare at me like that.
Yeah, because I'm just thinking, keep your opinion to yourself.
That goes both ways.
No, it doesn't actually, because I'm the one that's talking.
I can be talking to.
No, you can't. Because then people aren't going to hear me and you're going to be a distraction. Do you see how this works? I know. It seems so unfair. I know. I'm so sorry. All I want to do, I don't want to graph this one. I just want to practice setting it up. That's all. So there's a place in Alberta called Head Smashed in Buffalo, John. That's what it's called. It's a place where bison roam.
Oh.
Yeah, that's just what it's called. That's just what it's called. I mean, that's a lot of indigenous names or things like that. Okay. So when you go there, there's a interpretive center. The admission fee is $5 for a student, $9 for an adult. In 1 hour, 32 people visited the center, and a total of $180 in admission fees was collected. How can I translate this to a system? Remember, first of all, we need to establish our two unknowns. What are they?
X and Y.
Which represent what?
How many results?
How many students?
What?
How many adults? Yeah, that was an interesting one. Now, with these systems, you must always construct two equations. Give me one. The number of tickets, student and adults, must add up to 32. Why are you so rude? Anyway, the total, how about the second one? Yes, Ayla. Ayla, go ahead, Ayla. Ayla!
Yay! Ayla!
Okay, go ahead.
5x plus 9y equals 180.
Thank you. 5x plus 9y equals 180. So then you would see how you would have to solve it by graphing. Okay, again, it can be pretty complicated because first of all, you're going to have to solve your equations for y to get it in slope-intercept form. Then you're going to have to make sure to choose your proper scales. Then you're going to have to draw the lines. Then you're going to have to find the point of intersection, and it may not be exact. So this is kind of the drawback to graphing. I mean, I wanted to show you that we can use graphing as a way to solve it, but to be honest, it's not very efficient. Because in this last question, we didn't get the exact. We had to approximate. In this question, it's going to require a lot of work to graph these two and find the point of intersection. And again, we may not be exact. How we can be exact is when we use algebra, which are the last two methods that we're going to talk about next week. Okay? So I'm not going to finish this one. This one completed is on Teams in the notes. I just wanted to practice setting up the system. So that's everything.